Welcome to the ENM channel. In this series, we'll be focusing on the Electromagnetism Foundation, and we'll begin with the Electromagnetism Tree to give you a better sense of what to expect in the next episodes. Electromagnetism, and by its name, is formed of electricity and magnetism. Electricity, and by digging into its origin, is created by electric charges. Stationary electric charge produces an electric field around itself, and that is known as electrostatistics. By the same logic, magnetism, and by digging into its origin, is created by magnetic moment or magnetic charge, which is by its side generated by electrons' mobility around itself. When the magnetic moment is produced, a magnetic field encircling it will be produced too. Additionally, the magnetic field can be produced by the electrons' movement. When the electrons move around themselves, or in a linear direction, magnetostatics arises. When the electrons start to mobile in a sinusoidal direction, then we'll be having what's known as electrodynamics or electromagnetism, as the unification of electric and magnetic forces will be more obvious. The element that catalyzes the electrons to move and create electromagnetism is known as the electric potential difference, or voltage. When the electrons start flowing due to the voltage effect, the electric current is generated. By moving on, electromagnetism is directly affected by four elements, which they're conductivity, resistivity, permittivity, and permeability. These elements lead to the concepts of conductance, resistance, capacitance, and inductance, respectively. This is a short brief on the series, and we shall begin with electromagnetism, but that's left for the next episode. From the largest scale objects in the universe, such as galaxies, stars, planets, and Earth, to the tiniest scale particles, such as matter, molecules, and atoms, electromagnetism force interferes with them all. Electromagnetic force, as the name implies, is formed of electric and magnetic forces conveyed by the electromagnetic field. This force generates electromagnetic radiation, which is responsible for how we perceive the world with our eyes through light. Also, electromagnetic energy is the driving force behind the contemporary world's progress, as the discoveries and innovations of the 19th century and before paved the way for the advancement of electromagnetism applications and led to the birth of electricity, telecommunications, internet, and other technologies. Here's a brief on electromagnetism development. In 1600, the English scientist William Gilbert studied electricity and magnetism on amber, and he was the first to coin the term electricity. In 1785, Charles Augustin de Coulomb, a French scientist, published Coulomb's law. Alessandro Volta, an Italian scientist, created the battery around 1800. John Dalton, an English scientist, proposed the atomic theory in 1808. Carl Friedrich Gauss, a German mathematician, developed the electric and magnetic flux principles in 1813. Hans Christian Ørsted, a Danish scientist, demonstrated in 1820 that an electric field generates a magnetic field. In 1820, André-Marie Ampère, a French scientist, developed Ampere's law. George Simon Ohm, a German scientist, developed the concept of electric resistance in 1826. Michael Faraday, an English scientist, published the law of induction in 1831. In 1832, the electromagnetic self-inductance was discovered by American physicist Joseph Henry. In 1844, Samuel Morse, an American inventor, invented telegraphy and the Morse code. Gustav Kirchhoff, a German scientist, developed Kirchhoff's circuit laws in 1854. James Clerk Maxwell, a Scottish mathematician, published his electromagnetic field equations in 1865. Alexander Graham Bell, a Scottish inventor, developed the telephone in 1876. In 1879, Thomas Alva Edison, an American inventor, created a sustainable electric lamp, and in 1882 built the first DC power station. In 1888, the German physicist Heinrich Rudolf Hertz empirically confirmed Maxwell's mathematical calculations, proving the presence of electromagnetic waves. In 1893, the American inventor Nikola Tesla and the American entrepreneur George Westinghouse built the first modern AC power station. Guglielmo Marconi, an Italian inventor, established the first transmitting and receiving wireless station in 1895. In 1897, J.J. Thomson discovered the electron. That was an opening about electromagnetism. Around 2750 BC, ancient Egyptians noticed electricity through the shocks produced by electric fish, but without providing any logical explanation. Later, and approximately in 600 BC, Thales of Miletus was the first researcher into electricity, discovering that friction between ambers converts them into magnets. However, electricity remained an unknown phenomenon until the English scientist William Gilbert performed his experiment on both electricity and magnetism in the year of 1600. Through his research, he discovered that rubbing an amber produces static electricity. Then, he used the new Latin term electricis, a word derived from the Greek word electron, which means amber, to refer to the ability of attracting small objects when rubbed. And so, the English word electricity was born. So what is electricity? Electricity is a type of energy that may be described physically as a natural phenomenon linked with the existence and mobility of electric charges. These electric charges are properties of charged particles, such as electrons and protons, as they produce a force of attraction and repulsion amongst themselves. This force will lead to electric charges' motion, and hence, that motion is known as electricity. Electricity could be classified into two main types: electrostatics and electrodynamics. Electrostatic, in which electric charges are stationed in one area and have no ability to move, and when discharged, they discharge all at once, as in lightning. Or, electric charges have a constant motion that does not change over time, as in DC currents. Electrodynamics, in which the electrons' flow may change over time, creating by that a changing magnetic field like AC current. That was an introduction about electricity. Anything that has space, volume, and mass is defined as matter. Under this classification fall the massive objects like galaxies and planets, and small objects like sand and water drops. Plants and animals, even the humans, are no exception. Matter, and by its nature, is composed of atoms. An atom, by its side, is composed of nucleus and particles orbiting around it. The nucleus is composed of two main particles called protons and neutrons. The particle which are orbiting around the atom's nucleus are known as electrons. Early atom hypothesis attempted to determine the nature of the atom, as one of these hypotheses compared the atom to a watermelon, with the black seeds representing electrons. Others tried associating the electrons' movement around the nucleus to the planets moving around the sun, which later became known as Bohr model. The most precise theory was offered by quantum mechanics, which considered the electrons to be just like a cloud surrounding the nucleus. As previously stated, the atom is made up of protons, neutrons, and electrons. Protons and electrons both have an electric property, represented by the electric charge. However, neutrons do not. Protons are positively charged and electrons are negatively charged. While neutrons have no charge, naturally, The number of protons in an atom equals the number of electrons, and that leads the positive and negative charges canceling each other, resulting in an atom with no charge. Or, in other words, a stable atom. The electrons, unlike the protons and the neutrons, have the ability to mobile as they are orbiting around the atom's nucleus. This gives the electrons the advantage to travel from atom to another, leading by that to atoms denaturizing. If the electrons leave the atom, then the atom will be positively charged, as the number of protons and hence positive charges will be greater than the number of electrons. However, if the electrons are migrating to the atom, then the atom will be negatively charged, as the number of electrons and hence the negative charges will be more than the number of protons. When the atom gets denaturized, positively or negatively charged, an electric field is generated, but that will be discussed in the next episode. The atom normally is neutral and has no electric charge. However, when deneutralized, electric charge will be generated, charging the atom and producing an electric field around it. Here in this episode, we'll be discussing three major properties of the electric charge that shape the behavior of electricity, or in other words, the behavior of the electric field. First, the electric charge is monopole, either having a positive or negative pole. This means that objects when charged can be either positive or negative. Secondly, the stationary electric charge radiates field lines around it, generating by that a field of electricity, and that is how the electric field is created. If the electric charge is positive, then the field line's direction will be transmitted from the charge's center, and hence the electric field will be radiating outward. However, if the electric charge is negative, then the field line's direction will be transmitted towards the charge's center, and thus the electric field will be radiating inward. If there is no electric charge, then there is no electric field. The electric field could be defined as the electric force that is required to repel or attract a test charge. If two particles with the same charge approach each other, they'll be repelled. However, if these two particles have got different charge and get near to each other, then they'll be attracted. This force of repulsion and attraction is called the electrostatic force, which is governed by Coulomb's law, and that is the electric charge's third property. Additionally, the strength of the electric field depends on the total number of electric charges. As much they are as strong, the electric force would be. At this point, we have a stationary charge that generates an electric field, in which brings us to what is known as electrostatics. But that is left for the next episode. Electrostatic, or static electricity, is a kind of electricity in which the electric charges create an electric field and remain stationary in their positions, without initiating a current flow, or their current flow doesn't change over time. The first sort of electrostatics occurs as a result of an imbalance of electric charges within or on the surface of a substance, as positive and negative charges are separated on that surface. The polarity of this imbalance is measured by the electric constant known as permittivity or dielectric constant. By that polarization, and when the positive charges in one surface get close enough to the negative charges in the other, and vice versa, the static electric charges found in the two surfaces will be triggered to attract each other due to the electrostatic law of attraction, resulting in discharging in a form of a strike for a very short period of time. Note that the striking strength is proportional to the amount of charges presented on the two surfaces. Static electricity could be created also when certain materials are rubbed against each other, like wool on plastic or the soles of shoes on carpet due to the friction. This process creates electrons to be pulled from the surface of one material and relocated on the surface of the other material. A static shock happens when the surface of a substance, which is negatively charged, comes into contact with a positively charged conductor, or vice versa, similar to the small charge you get after walking on carpet and touching the door handle. The other source of electrostatics is created when electrons flow in a steady way in a form of direct current. This type will be covered in later episodes. At this point, we shall shift to magnetism, as most of the essential factors of electricity have been introduced, but that is left to the next episode. Around 2,500 years ago, ancient Greeks learned about magnetism from lodestones or magnetite, which are naturally magnetized pieces of iron ore. The word magnet was adopted in Middle English from Latin magnetum, meaning lodestone, ultimately from Greek magnetis lithos, meaning magnesian stone, an ancient Greek city where lodestones were found. Microscopic examinations revealed that lodestone is composed of magnetite with inclusions of megamite, as well as impurity metal ions of titanium, aluminum, and manganese. So what is magnetism? Magnetism is a form of energy that may be described physically as a natural phenomenon associated with the presence of a mobile electric charge that creates a magnetic moment as a result of its mobility. The magnetic moment by its side spins around the electron, generating magnetic field lines or magnetism. Magnetism could be classified into two types: magnetostatics and electromagnetics or electrodynamics. First, magnetostatics of ferromagnetics, where magnetism is generated naturally as the electrons are spinning around themselves in the same direction, causing electric current flow and hence creation of magnetic moment. This property is found in specific materials, granting them a stronger magnetic effect, such as iron, nickel, and cobalt. The magnetic effect on the materials could be classified under three main types: strongly attracted materials by the magnetic field, such as ferromagnetics; weakly attracted materials by the magnetic field, such as paramagnetics; non-attracted materials by the magnetic field, such as diamagnetics. In addition, magnetostatics can be generated artificially in the form of static magnetic field, as the electric current flows in a linear direction without changing over time. Magnetic resonance imaging, MRI, is an example of this. Second, electrodynamics or electromagnetism, in which the electrons' flow may vary over time, creating by that a changing magnetic field. AC generator is an example of this type. That is a brief introduction about magnetism, and the primary element of it will be introduced, but that is left to the next episode. Matter, as discussed in the previous episodes, is made up of atoms, and an atom is composed of protons, neutrons, and orbiting electrons. Protons and electrons have an electric property represented by electric charge, while the neutrons do not. For magnetism, the story is a bit different, as all atoms' elements, protons, electrons, and even the neutrons, have a magnetic property represented by magnetic charge, or in other words, magnetic moment. The magnetic moment is generated due to the elements spinning. But hold on for a second. Do the proton and neutron spin, or even have the ability to move? Has not been mentioned that these two elements are stationed in their posts. Well, the movement of protons and neutrons are classified under particle physics, and that topic shall be introduced in the upcoming series. But the element that we care about now is the electron and its mobility. The electron, and due to its mobility around itself, generates a torque in a form of weak electricity current, producing a magnetic moment in a form of magnetic field, and that's what gives rise to magnetism. Electrons' mobility happens in two forms: around atom's nucleus and around itself, similar to how the Earth orbits around the Sun and itself. Furthermore, the electron may spin around itself in two directions. clockwise and counterclockwise. The magnetic moment generated due to the electron's orbit around the atom's nucleus is too small comparing to the element's intrinsic magnetic moment produced due to its spinning around itself. So the nucleus's magnetic moment could be neglected as it will not be considered for this series. As a result, we can conclude that the atom has electric energy stored in its protons and electrons, creating an electric field, as well as magnetic energy stored in its electrons, creating a magnetic field. In the next episode, the concept of magnetic field will be introduced. In the previous episode, the magnetic moment development was introduced. But what are the properties of a magnetic moment, and how the magnetic field is produced? Here in this episode, we'll be discussing the three major properties of the magnetic moment that shape the behavior of magnetism, or in other words, the behavior of the magnetic field. First, the magnetic moment is a dipole, meaning by that the magnetic moment has two poles south and north, which are generated simultaneously due to the electron spin. A monopole magnetic moment is a non-existent hypothetical fundamental particle. Second, the mobile electron catalyzes the magnetic moment to radiate field lines around it, creating a field called the magnetic field. If the magnetic moment's pole is north, then the field line's direction will be transmitted from the pole and hence the magnetic field will be radiating outward. However, if the magnetic moment's pole is south, then the field's line's direction will be transmitted into the pole, and thus the magnetic field will be radiating inward. The magnetic field could be defined as the magnetic force applied on a mobile charge, perpendicular to the charge velocity. The force of repulsion and attraction is also true for magnets, which is also governed by Coulomb's law. Assume two magnets with the same polarity come into contact, then they repel each other. When two magnets with opposite polarities come into contact, then they attract each other, and that is the magnetic moment, third property. In addition, the magnetic field is produced by the spin of the electron around itself, as the produced magnetic field depends on material chemical bonds that control the electron's arrangement. Also, the magnetic field can be generated by the electric current flow, as the produced magnetic field depends on the electric charge's quantity, velocity, and acceleration. At this point, we have a steady mobile electric charge that generates electric field and a magnetic field that is constant over time. This brings us to what is known as magnetostatics, but that is left to the next episode. Magnetostatics, or static magnetism, is a kind of magnetism in which the electrons spin around themselves, or making a constant current flow in one direction, which does not change over time, creating by that a static magnetic field. The first sort of magnetostatics is generated by the electron spin. Because the electron spins around itself by nature, it creates a rather modest current. This current creates a magnetic moment, which generates a magnetic field, as previously stated. Permeability is the magnetic constant that measures the magnetism induced by the electron spin. If the permeability value is 1 or less, the material is diamagnet. If the value is greater than 1, the material is paramagnet. And if the value is 130 or more, the material is ferrimagnet. Diamagnetic objects are materials which oppose the magnetic field direction and weakly repel by it. Diamagnetic substances have equal number of electrons that spin in opposite directions, so their magnetic effect is cancelled out. These materials are rarely getting magnetized, and when the magnetization source is removed, their magnetization is lost. Silver, lead, copper, and water are examples of these materials. Paramagnetic objects are materials which do not oppose the magnetic field and weakly attracted by it. Paramagnetic materials have some electrons spin in one direction and some electrons spin in an opposite direction, resulting in having a small magnetization. These materials can be magnetized, and when the magnetization source is removed, their magnetization is lost. Air, nitrogen, and aluminum are examples of paramagnetic. Ferromagnetic or ferrimagnet objects are materials which do not oppose the magnetic field and strongly attracted by it. In these materials, the majority of the electrons spin in the same direction, so their magnetization is significant. The atoms in these compounds are extremely magnetic, but they're not yet magnets. Cobalt, nickel, and iron are examples of ferromagnetic. The other source of magnetostatics is created when electrons flow in a steady way, in a form of direct current, DC. An example of this type is the MRI, and the magnetic storage used particularly for computer memory, such as hard drives. Now that we have covered electrostatistics and magnetostatistics, we shall move on to introduce electrodynamics or electromagnetics. But that is left for the next episode. Electrodynamics, dynamic electricity, or electromagnetism is the other type of electricity and the other type of magnetism, where these two forces are united together, in which the electric charges are in an alternating motion, creating a magnetic field changing over time. When the electric charges are subject to a time-varying force, the charges begin to flow, resulting in electromagnetic work represented by a time-varying current, flowing in a directed direction. In contrast to the static situation, the charges are continuously changing their location depending on how quickly change their locations with respect to time, as that leads to the frequency principle, which will be explored in later episodes. As a result of the charges' alternating movement, an electromagnetic field is generated, which is composed of electric and magnetic fields perpendicular to each other, leading to what is known as electromagnetic force. This force is described by Maxwell equations and governed by Lorentz law. The electromagnetic force gives rise to the electromagnetic radiation, as this radiation constitutes the electromagnetic spectrum on which various types of electromagnetic waves and visible light rely. The electromagnetic radiation had been proved experimentally by Heinrich Hertz. In general, the electromagnetic interaction is considered as one of the four basic forces of nature, together with the gravity, weak, and strong interactions. In the following video, we will be discussing the concept of the electric potential difference and how does it bridge the electric charge to the electromagnetism. But that is left to the next episode. So far, we've been introduced to the concepts of electric charge and magnetic moment, which are the foundations of electricity and magnetism. Electrostatic, magnetostatic, and electromagnetism concepts have also been addressed. But what does transform these properties and concepts into applications? This question will be answered in this episode. To generate electromagnetism, the electric charge must be catalyzed to mobile. This mobility is performed by applying electric work on the electric charge, releasing its intrinsic electric potential energy. But hold on a second. What's energy and what's electric potential energy, and how that work is applied on the electric charge? Well, let us start with energy. Energy is conserved quantity that can neither be generated nor destroyed, and it's measured in joules. In general, energy has two fundamental forms, potential and kinetic, as all other types of energy may be classified under these two categories. Moreover, potential energy is the energy that's stored within an object's field. When an external field exerts force on that object, a work will be done causing the object to release its stored potential energy and convert it into kinetic energy, like how the electric field causes charges to attract or repel each other. The magnetic field that causes magnets attract and repel each other. The gravity field that causes the ball to fall down. The chemical bonds that cause the match to burn. The mechanical formation that causes the spring to stretch and compress. Based on that, and since the electric charge generates an electric field, then the electric potential energy is stored in that field. So in order to release the electric charge's potential energy to initiate its mobility, an electric work, or in other words, an electromotive force, must be applied. The electromotive force, or EMF, could be achieved by chemical reaction, mechanical motion, nuclear radiation, solar radiation, or other types as it converts them into electric energy. Once achieved, EMF will create and maintain an electric potential difference by separating positive and negative charges into two distinct regions. The greater the gap difference, the greater the electric potential, as the EMF will be at its peak when the circuit terminals aren't connected. When the circuit's terminals are connected to a load, the electric potential difference between the charges starts to shrink, transforming electrons' potential energy into kinetic energy, which leads to pushing the electrons from terminal to another, resulting in electrons' motion in the circuit and to the gradual consumption of the EMF. When the EMF is totally consumed, the difference between the charges will disappear, and as a result of that, electrons' flow will be interrupted. Electric potential difference, which has been created by electromotive force, or EMF, to catalyze the electrons to flow between circuits' terminals, is also known as voltage. Voltage is the main reason behind electrons' motion in electric circuits, and hence the main reason behind the operation of all the electric and electronic devices that we know. At this point, the element behind electrons' mobility When electrons begin to flow through a conductor as a result of the voltage effect, each electron passes through the conductor per 1 second, creates 1 ampere of electric current. The strength of the electric current depends directly on the strength of the voltage and the weakness of the resistance, according to Ohm's law. In addition, every material has a certain level of resistivity and conductivity. The resistivity prevents electron passage, whereas the conductivity enables it. Silver, copper, and aluminum have low resistivity and high conductivity compared to other materials. Therefore, these 3 materials are the most commonly utilized in electric applications. The flow of electrons, often known as electric current, is divided into 2 main types: direct current, DC, and alternating current, AC. The electrons in DC current flow in a single, uniform direction and do not vary over time, and that gives rise to electrostatistics and magnetostatistics. However, the AC current gets its name from the fact that electrons mobile back and forth in 2 different directions, changing over time and forming a sinusoidal circle of 360 degrees, which gives rise to electromagnetism. The generation of DC current depends on how DC voltage is produced, as it could be obtained by battery, solar cell, or dynamo. Likewise, the generation of AC current depends on how AC voltage is produced, as it can be obtained by alternator. Since the DC current flows in a single, uniform direction and does not vary over time, it operates the electric appliances in a stable way. Unlike the DC current, the AC current moves back and forth in a bidirectional fashion. Thus, its strength doesn't remain constant over time. Therefore, it must flow in a way that its strength is maintained in its operating mode, so the appliances can operate. If the AC current runs for 1 cycle per second, the electric appliances will not operate, as the current passing through is similar to the light bulb when it's blinking in a very slow manner. If the AC current runs for 5 cycles per second, the electric appliances will still not function, as the current passing through is similar to the light bulb when it's blinking, but a bit faster. If the AC current runs for 45 cycles per second, the electric appliances will start partially to operate, as the current passing through is similar to the light bulb when it's blinking in a fast mode, where that blinking might be detected by the human eye. If the AC current hits 50 or 60 cycles per second, the electric appliances begin to function smoothly, as the current passing through is similar to the light bulb when it's blinking in a fast mode, where the blinking couldn't be detected by the human eye. If the AC current runs for 100 cycles per second, the power losses would be considerably greater and might harm the electric appliances, as the current passing through is similar to the light bulb when it's blinking in a very fast mode, where that blinking couldn't be detected by the human eye, rather harming it. In short, how many cycles make the current per second is known as frequency, and it's measured in hertz. Additionally, voltage and current are affected by 4 elements, which are conductance, resistance, capacitance, and inductance. But these elements will be covered in the next episodes.
3, 2, 1.
The ability that allows the electric current to flow is referred to as electric conductance. Electric conductance is directly associated with material electric conductivity, where it can be low or high depending on the atomic structure of the material. The material or the object that allows electric current to flow is called a conductor. Metals, electrolytes, superconductors, semiconductors, and plasmas are all examples of conductors. However, in this video, we'll focus on metal conductors. Silver has a higher electrical conductivity. Copper has a high conductivity, though it's weaker than the silvers. Aluminum has lower conductivity when compared to the previous metals. By examining the atom's fundamental structure, the conductive substance and its structure may be recognized, more specifically in conductive materials. The atom's final orbit, the valence shell, typically has one or a very small number of electrons. This indicates that these electrons are weakly connected to the atom and, as a result of their high mobility, can readily leave their positions when energy is applied. Because of that, the atom's chemical structure will have more cross links that will allow the transmitted electrons from passing when energy is applied, and hence, more electrons can pass freely. A material's conductance is determined by a number of factors, including, firstly, material conductivity, which is determined by the crystal structure and chemical composition of the material, how loosely the electrons are bound to the atom. The higher the mobility would be, and hence, the higher the conductivity. Also, as much the crosslinks found on the material structure that allow electrons from passing, as much the conductivity would be. As a result, only a little amount of energy is necessary to move these electrons from one atom to another in such substances. Second, the geometrical structure formation. When the length of a material is reduced, the material conductance increases, and when the cross-sectional area of that material is increased, the material conductance increases, and vice versa. Material conductance is measured in Siemens. while material's conductivity is measured in Siemens per meter. That was the first element. The ability to block the electric current flow is known as electric resistance. Electric resistance is directly associated to the material electric resistivity, where resistivity can be low or high depending on the atomic structure of the material. The material or the device that opposes and resists the electric current is also called a resistor, isolator, or insulator. The common resistor comprises two passive terminals and a resistive substance composed of an electric insulator with a very high resistance and poor conductivity placed between them. The resistor's terminal allow the electric current to passing through the resistive substance, so it's reduced. An example about insulators is quartz, sulfur, mica, and rubber. By examining the atom's fundamental structure, the resistive substance and its structure may be recognized. More specifically, in resistive materials, the atom's final orbit, the valence shell, typically is full or nearly full of electrons. This indicates that these electrons are tightly bound to the atom and, as a result of their weak mobility, can hardly leave their positions when energy is applied. Because of that, the atom's chemical structure will have less cross links that will allow the transmitted electrons from passing when energy is applied, and hence, less electrons can pass freely. A material's resistance is determined by a number of factors, including, first, material resistivity, which is determined by the crystal structure and chemical composition of the material, how tight the electrons are bound to the atom. The lower the mobility would be, and hence the higher the resistivity. Also, as less the crosslinks found on the material structure that allow electrons from passing, as higher the resistivity would be. As a result, a higher amount of energy is necessary to move these electrons from one atom to another in such substances. Secondly, the geometrical structure formation. When the length of a material is increased, the material resistance increases, and when the cross-sectional area of that material is decreased, the material resistance increases and vice versa. Materials resistance is measured in ohm, while materials resistivity is measured in ohm per meter. That was the second element. Capacitance is defined as the capacity to store electrons in form of electric field while opposing voltage changes. Also, capacitance is directly associated to the material permittivity, where it could be low or high, and according to the material formation. The device that stores electrons is called a capacitor. To build a common capacitor, two parallel metal conductors separated by a dielectric material and insulating material must be used. It should be noted that different shapes can be used too. Also, one plate cannot be used as it will cause the circuit to be shorted. According to the previous mentioned fact, every element in this universe is neutral by nature, since its positive and negative charges are equal in numbers. However, when an external voltage is applied to the capacitor plates, the transmitted electrons begin to repel the existing electron found on the first and second plates, according to Coulomb's law. The first plate begins to absorb the transmitted electrons and distribute them evenly throughout its surface, and pushing the electrons located on the second plate toward it. In this place, the majority of electrons are collected in the first plate, surpassing the original amount of metal protons and therefore becoming negatively charged. Due to the initial amount of metal electrons being pushed toward the first plate, the second plate will only have its original number of protons, leading the plate to be positively charged. When the first plate is saturated, no more electrons can pass across it, and so the charges are stored. That charge storage creates a potential difference between the two plates, which can be utilized when the primary voltage source is run off. Direct current does not pass through the capacitor because of the dielectric, as it flows in a linear direction. However, alternating current can flow through the capacitor, bypassing the dielectric, as it flows in a sinusoidal manner. The role of the dielectric found between the capacitor plates is to polarize them, enhancing the separation of the positive and negative charges from each other when external voltage is applied. Ceramic is an example of dielectrics. There's some factors that influence the capacitance strength, such as, first, dielectric material permittivity. As larger the permittivity, as larger the capacitance. Second, geometrical formation. As smaller the distance between capacitors' conductors, as larger the capacitance. As larger the sectional area of the capacitor's conductors, as larger the capacitance, and that means more charges to be stored. The geometry of the capacitor, which its capacitance differs from shape to another. Material's capacitance is measured in farad, while material's permittivity is measured in farad per meter. That was the third element. Inductance is defined as the ability to store moving electrons in a form of magnetic field while opposing current changes. Also, inductance is directly associated to the material permeability, where it could be low or high and according to the material formation. The device that stores electric current is called an inductor. The inductor is consisted of a magnetic core and a coil. The coil is made of a conducting winded material, such as copper or aluminum, wrapped around the core. The core, on the other hand, is made of a magnetic material, such as air or iron. Essentially, the core of an inductor, and according to its permeability, increases the inductor's inductance, as it could be air or ferromagnetic. The inductor's core shapes can also vary, as it could be toroidal, rod-shaped, or even nothing but air. In addition, copper wire is mostly employed as the winding material in inductors. This wire is winded many times to form a coil. The purpose of this winding is to enhance the magnetic field strength by getting the electrons passing across numerous ends rather than only two ends, which results in enlarging the magnetic field across the inductor and hence increasing its inductance. When an electric current starts running through an inductor, the inductor initially shows some resistance to the flowed electrons. This resistance is caused by the inductor as it starts absorbing the flowing electrons, generating by that a magnetic field across it. When the inductor is saturated, the resistance will disappear and the inductor starts acting as a normal wire. When the external current source is eliminated, the inductor releases its stored energy in form of significant voltage discharge, aiming to stabilize the electric circuit. In other words, the inductor is continually working on keeping the electric circuit stable. Since the alternating current is frequently changing, then the inductor will continually be impeding and preventing it from passing through it. However, and since the direct current does not change over time, then it passes through the inductor, creating a constant magnetic field. There are some factors that influence the inductance strength, such as, first, core material permeability. As larger the permeability, as larger the inductance. Second, geometrical formation. As greater the turns of coil, as greater the inductance. The geometry of the inductor, which its inductance is increased when the wire is shaped as a coil or helix. Material's inductance is measured in Henry, while material's permeability is measured in Henry per meter. That was the fourth element that has an effect on the electric circuit. Also, the final episode of this series. We hope that you enjoyed it and got an idea about Electromagnetism Foundation. Wait for the next series and ensure that you're subscribed and click the bell icon. Please help us by liking, commenting, and sharing. This encourages us to deliver more. Wait for the next video on the Electricity and Magnetism channel, and we'll see you in the upcoming series.